I'm setting up the YouTube live.
Okay. You'll do the recording, yeah?
Yes. Have you been to Moscow?
Me?
Yes.
No. I would like to go, though. Actually, I would like to go to St. Petersburg.
So how have you been, Ryan?
Good. I got my second shot yesterday, but I'm feeling fine so far.
Oh, you mean what do you mean by why second shot?
For the COVID vaccine.
But why second?
Because I got the Pfizer and it's 2 shots.
Oh, I see.
You have to take 1 shot and then wait a while and then take the other one. And most people say after the second one, you feel like a slight fever. So we'll see. It hasn't hit me yet, though. It might not.
That's great. Do you know where it is? This place?
No, I don't recognize it. What is it?
Moscow State University, I think.
Oh, wow.
The main building.
It's a beautiful campus. Hi, Anton.
Welcome, Anton. Anton, you are co-host, and then you can test and share the screen. You can start the screen sharing. On multiple accounts, then I will also aid others if there's any.
Is muted. Hi, Ryan. Hi, Joanne. I didn't realize I was muted.
How are you?
Good. Share the screen then. By the way, how are the arrangements in Harvard? Are you guys allowed to come to your offices, and is everything more or less back to
I
normal?
think the CMSA is still closed, right, Juven?
Yes, it is
Yeah.
closed.
I'm in Los Angeles
Oh, I see.
at my parents' house. So
I feel this suggests a future way for theoretical physicists to work. We can travel around the world and still work. We don't need to be associated with a fixed institute. I think that would be the best. So it'll be great. We can travel to Moscow and still work. Pay by, I don't know. As long as there one institute can pay us the salary, I think we can just travel everywhere.
some combination of Zoom seminars and actually going to visit collaborators.
Yeah,
would be ideal.
Yeah, I think well, conferences, a real conference is still better, and the workshop's better than Zoom workshops. If you talk to people afterwards.
And actually, even nowadays, a lot of lectures are Zoom recorded and put on YouTube. So I feel like actually professor may not need to teach a course multiple times. It can just be Zoom recorded and put on YouTube. And then you just need to hold office hour. Students go to listen or watch the lectures, and you just hold the office hour to answer a question or maybe some more details. And they can save a lot of professor office, this working hours, and then you can do more research.
So let's wait like 2 more minutes for people to arrive, and then I'll introduce you. We can get started.
Anton, is your background a real physical shelves or it's not? Right? Yeah, it's not. Sorry.
No, my makeshift office doesn't look anything like this.
And when I was at IIS, I checked a lot of those books at the library. Many of them has signed by you. You have a check out many books. A lot of IIS libraries book where you have put your signature in the back. You have a sign.
Yes, a lot of time over.
Yeah. So maybe you keep a lot of books or read a lot of books.
Yeah, I remember.
Yeah, there are many of them.
Made quite a friend with a librarian because I was there all the time.
Okay, let's begin. So welcome everyone to the CMSA Quantum Matter and Math and Physics seminar. Very happy today to have Professor Anton Kapustin from Caltech, who is visiting us virtually. And he's one of the movers and shakers in this field of mathematical physics and quantum matter, and is responsible for this cobordism classification of SPTs, among other things, and earlier important work on supersymmetric gauge theories and string theory. And today he's going to tell us about his work on chiral edge modes, thermoelectric transport, and the third law of thermodynamics. So thanks very much.
Thank you, Ryan. It's a pleasure to give a talk at CMSA, which I visited several times, but in real life, not virtually. So today I'm going to talk about some subject which is in some sense very old. So much of it is related to theory of linear response and transport, really ancient stuff. Because you want a starting point probably goes back to Ohm, like in 1820s. So, but surprisingly, I found that the more I learn about it, the less I understand. So, some of this, as I discuss later, some of the foundational issues I think still not understood. But my immediate interest was actually in something more esoteric, topological invariants of gap two-dimensional materials. So I'll frame this talk as discussion of two-dimensional materials, but in reality, many of the issues, are just as very similar issues exist for three-dimensional materials. So what are the topological invariants if you look at materials with an energy gap? Well, I'll start, so the most familiar one is the Hall conductance. So specifically Hall conductance at zero temperature. So at non-zero temperature is not a topological invariant, but at zero temperature, it's something which is an invariant of a phase of gap 2D matter. So, but it's defined when you have unbroken U1, whatever that means. So I don't want to get into the details, but of course, the situation is different in superconductors, so we don't want to discuss that case. But I put first not this familiar invariant, but rather thermal Hall conductance, which is describes. Well, I'll later discuss how exactly these transport coefficients are defined. But for now, it just tells you how situation when the heat flows perpendicularly to the temperature gradient. And I put it first because that's supposed to be defined for any gapped material, whether it has broken or unbroken U1. So in some sense, the most basic gapped invariant, but actually also not very well understood. So specifically, it actually vanishes at zero temperature, but its slope at zero temperature is non-zero in general, and that's the topological invariant, the slope of this thermal Hall conductance. Now I want to focus on these, but of course there are others. There are also invariants of phases which are not so easily described. So these two invariants are something essentially classical, like conductance. Well, Hall conductance certainly goes back to the 19th century, and thermal Hall conductance probably also goes to the 19th century. So, but this anionic invariance relate to the fact that there are non-trivial topological non-trivial excitations sometimes in two-dimensional materials, and you can extract additional invariants from properties of those related to braiding and fusing. So I don't want to discuss those; they're more complicated. And the first, And there's also a class of materials where there are no such excitations at all. They're called short-range entangled materials. And for those, these kind of transport coefficients are the only ones which are relevant. So the first question I want to ask is actually, are these the only topological invariants associated with transport in two dimensions in gap materials? So so this Hall conductance is purely electric property. The thermal Hall conductance is a purely thermal one, and perhaps there's also something mixed, because we know there are also various effects like Seebeck Peltier effect, which sort of mix electricity and thermal properties. Maybe there's something there too. Now, since nobody ever seen any, so the answer is probably not, but we'd like to understand why precisely. So, and we actually, well, so there's a recent paper which, with Michael Levin from the University of Chicago and a graduate student at Caltech, Lev Spodinenko, which discusses precisely this question. And that's going to be the part one of my talk. I'm just going to discuss why there are no invariants associated with mixed sort of thermoelectric phenomena, while there is just there's only thermal Hall conductance and Hall conductance. And the second part of the talk will be more general discussion of thermoelectric transport, because, well, we don't actually have a completely satisfactory proof that these invariants don't occur. So they don't exist. Satisfactory, I mean like essentially something approaching mathematical rigor. The most naive approach would be just to start with microscopic formulas for all these transport coefficients. And just ask, okay, can we see why some of them just must vanish as temperature goes to zero? Or maybe even exponentially small as temperature goes to zero. But turns out these microscopic formulas are very subtle. And in fact, there are lots of errors in the literature about what these formulas should look like. So that's why I'm not focusing on those. I don't starting with those. I'll start with some more pedestrian, well, and less rigorous approaches. So what is the problem? Let me state more precisely what the definition of this transport coefficients. So I want to consider some two-dimensional piece of material. So it's a view from above. So it's in orange. And I can create, well, so this is the edges. This is the two edges. Well, it's a material assumed to be sort of infinite in this direction. And I create some temperature differential between bottom and top parts of the material, and also perhaps some drop of, well, change in electrochemical potential. So between top and bottom. And well, since material is finite in this vertical direction, the current can only flow horizontally. In general, it will flow horizontally, and these various transport coefficients are determined. Well, in linear response, you assume that the particle number current, well, and energy current are proportional to these drops of chemical potential and temperature, or electrochemical potential and temperature. And the coefficients are called Hall conductance, thermal Hall conductance, and these two other coefficients, which for some reason remain nameless. So people call them sometimes transverse thermoelectric coefficients. I call them, even notation is not like generally established. I just picked some name nu and eta, because these kind of effects, transverse thermoelectric effects, were discovered by two guys named Attendability and Nernst. And so the generation of particle number current, electric current, when you have temperature gradients, known as the Nernst, in the transverse direction, called sometimes Nernst effect. It's a sort of, we might want to call it Nernst coefficient. And this we might call Attendability coefficient. That's why it's eta. But in practice, people mean something else by Nernst and Attendability coefficients. I'm not going to use these names. Just call them eta and nu. Now, if you have a gapped material, then at low temperatures, there are no excitations in the bulk. So the bulk currents should be exponentially suppressed. However, edge currents may be unsuppressed. So might be some stuff propagating on the edges, some gapless stuff. And that's what in the end leads to possibility that T equals 0 limit of this transverse coefficients may be non-zero. So specifically, when you have a non-zero T0 temperature limit of the whole conductance, you have quantum Hall effect, and when you have non-zero limit of this ratio, then you say you have a thermal Hall effect. And turns out that one can show that actually these limits are topological invariants in the sense that they don't change when under deformations of the system, which do not close the gap. By the way, intuitively, like, why should I divide by T here but not there? Well, it's simply an issue of dimensional analysis. Sigma xy is dimensionless, while kappa xy, you can easily check, has a dimension of energy or temperature. So divide by temperature, so it's plausible that it would be weird to have a topological invariant which is a dimensionful number. So if you divide by T, then it's dimensionless and it's more plausible than it could be a topological invariant. Okay, so the question I want to pose in this first part of the talk is whether one can have sort of a quantum Nernst effect, namely when the limit of this transverse thermoelectric coefficient is non-zero. It's dimensionless, so that will be the natural quantity to consider. Similarly, you can ask whether it could have quantum Etingshausen effect, that is generation of an energy current by electric field in the transverse direction. And this guy is dimensionful, and again, if you divide by temperature, you get something dimensionless, so it seems reasonable to postulate that perhaps this limit could be non-zero, and then one can actually show it's a topological invariant if it's non-zero. Now, in fact, one can easily see that this, well, I already said that bulk currents presumably exponentially small for a gap material. You can ask, okay, is it possible to interpret this net currents purely in terms of edge currents? That's a bit actually non-trivial, because if you have some excitation on the edge, this current must depend only on the temperature on that edge, and similarly on the other edge, right? So it turns out that if you want to rewrite this net currents as a sum of contribution of edge currents, then this only works, well, if this limit's actually the same. So in the very beginning, so we really have only one invariant, not two, one potential extra invariant. Okay. So, and specifically, if you assume that's the case, then you can actually get the formulas above by postulating the following forms of edge currents. So, so the edge current should be proportional to the, well, for the electric current, proportional linear function in both chemical potential and temperature, and for the edge current, quadratic in both chemical potential and temperature. And this nu and eta, well, there's only one guy. There should be like a coefficient in cross terms. So we know, well, coefficient here is simply that, precisely that limit. So we know that these guys could be non-zero. One can construct example just out of free fermions. But for free fermions, one can show that this actually always zero. So the question is maybe well, maybe if you turn on strong interactions, you could have this non-zero, or maybe not. Now, why do I say that these are topological invariants?
Anton, may I ask you, looking at this formula, it looks like this first line, it is derivative over mu from the second line. Is it accidental?
No, but I don't really, I cannot really derive it in this way. So, yeah, so, well, in a sense, yes. Well, the point is that the edge car, okay, so, well, this it's basically, well, okay, it's related to gauge invariance condition. If you look at the energy current minus mu times the electric current, that's supposed to be gauge invariant.
Mm-hmm.
So that's part of it, but that's not all of it. Yeah. But it's not quite. You see that like this guy, yeah. So that depends the mu dependence, right? If you differentiate this with mu, you're going to get the first line.
Yeah.
Gauge invariance, which requires it. I mean, the edge current is not gauge invariant.
Mm-hmm.
And okay, the electric current, sorry. Right. So yeah, this extra piece here,
Yeah.
you cannot get this way. So where did this come from? Why do I say it's topological? This is topological invariance, obviously. Well, suppose I have a material which is inhomogeneous. Suppose I like have some deformation of the Hamiltonian, which is known by this green shading here, but deformation which doesn't close the gap. There's still no bulk currents. So then, and suppose now suppose I have a slightly different setup in homogeneous material, but now identically the same temperature and chemical potential on both edges. On one hand, I can compute, so now that qualitative different edges, and I can apply the same formulas to compute them, but the net current has to vanish. So assuming that's the case, if the net current is supposed to vanish in equilibrium, then all transport coefficients which occur here, all these four guys, should be identical for this edge and for that edge, even though the Hamiltonians are different by varying some parameter. So that's why this topological invariant. That follows from, for the statement that you cannot have net energy or electric currents in equilibrium. So that's actually a very general statement. And for electric currents, it was stated and sort of given by hand-waving proof by Felix Bloch in 1933, some very obscure publication, some proceedings of some seminar by Brillouin. And Bohm gave a more careful proof in the Continuum in 1949, David Bohm. Now, interestingly, this proof doesn't work for energy current, even though intuitively it seems clear that you cannot have equilibrium currents of any conserved quantity. So there's so Lev and I actually wrote a short paper on this a few years ago, explaining how to give a different proof. Proof of this fact. Incidentally, yeah. So the reason, also Bloch actually thought about this problem was because at that time, some people thought that superconductivity, in particular persistent currents in superconducting rings, are just equilibrium currents, and they said that well, perhaps there is some non-trivial, some weird superconductors, a weird material where you can have a non-zero flowing current, macroscopic current, even though you're in equilibrium. I think Landau was actually one of the people who thought in that direction, but Bloch explained that this cannot be true. In reality, when you have a large ring, then if you're in equilibrium, that the current will be approach zero at the size of the ring. If it doesn't approach zero, it means you're in some sort of metastable state. Okay, so anyway, so now I want to argue though, well, since nobody's seen this invariant, thermoelectric invariant, maybe it's not there. Maybe it's always zero. So I'll give you, well, I'll sketch three arguments. And at first seems very easy. So the first argument, well, maybe not the most general one, but suppose you have a description of the edges by some sort of chiral conformal field theory. That's the standard assumption. Now that may not be true in general, like when you have disorder, actually in general, definitely not true. But suppose you have a clean edge, so you have a conformal field theory. So then the usual reasoning, something like this. So these anomalous edge currents, anomalous, by the way, why they call them anomalous suddenly? Well, because it's weird to have currents which are non-zero in equilibrium. As I said, for net current, if you have an actual isolated one-dimensional system, true one-dimensional system, that cannot happen by this Bloch's theorem and its generalizations. But here we're dealing with an edge of a 2D system, really. And on an edge, it can happen. So, but anyway, it's some sort of anomaly. So, well, the usual reason is something like this. So, these anomalous edge currents I explained within conformal field theory by anomalies in conformal field theory, more specifically this at-Hooft anomalies. And then those anomalies you can try to classify by saying, well, any anomaly can be sort of canceled by inflow from the bulk by using some sort of topological action in the 2+1 dimensional bulk. And these actions are easy to classify you put easy in quotes because, of course, as usual, you need to put in some very strong assumptions to make it easy. And it's not clear when they're true. But anyway, if you assume you have a topological action, then there are two obvious candidates for this action. There's a Chern-Simons action, which depends only on electromagnetic field. And you have a gravitational Chern-Simons, which depends only on the Levi-Civita connection on some external gravitational field. And the law is that the coefficient here is related to sigma xy at 0 temperature. The coefficient here is related to thermal Hall conductance, or rather its slope at 0 temperature. And there are no mixed U1 gravitational actions, and therefore, presumably, reversing this logic here, no mixed anomalies, and therefore this mixed coefficient should be 0.
Anton, can I make a quick and probably obvious comment here?
Yeah.
So I guess we don't necessarily have to invoke the bulk, right? The anomalies in CFT, in particular, the two you just mentioned are captured by the JJOPE and the TTOPE.
Yeah. I'll say it on the next page. Yeah.
Oh, okay. Yeah, I was
So
just
I don't,
about to say that the TJOPE generally can emit an anomalous term, but that would violate unitarity.
yeah, right. You're right. So you're absolutely right. So this argument, I don't like this argument, even though you can find sometimes like some arguments like this in kind of my literature, because first of all, yeah, this last part is really suspicious. For one thing, it's not clear to me, for example, why you can use field theory at all to describe well, the bulk. And second, more importantly, in the case of gravity, it's not unclear what this term has to do with thermal Hall conductance. This describes the response of a system to a background gravitational field. Nobody can ever tell me how to couple a gravitational field to say some lattice system. It's just ill-defined. There's just no procedure for deciding what this action is going to be for, say, lattice system. So this gravitational Chern-Simons in relation to thermal Hall is it's something which is not really understood. So that's what I'm saying here. So not clear how to relate these topological actions depending on metric to thermal properties. And by the way, it's also not true really that every anomaly in almost one dimensions corresponds to a bulk topological action. So as you just mentioned, as Shahan just mentioned, indeed there are mixed U1 gravitational anomalies in non-unitary conformal field theories. So namely, they manifest themselves as these singular terms in the OPE of a stress energy tensor and the current. So they do lead to mixed U1 gravitational anomalies, specifically to Gauss number non-conservation in that context. But they do not correspond to any bulk action. And in general, it's kind of, I'm not sure why this happens, but anyway, so there's no general rule that any anomaly can be represented by some absorbed by a bulk action. However, it is indeed easy to show that this coefficient alpha must be 0 in any unitary 1+1 dimensional CFT. And presumably, we have a physical system with an edge. That edge is described by unitary CFT. So one can show, well, and because of this, so using OPEs, if you say that this guy is not there, then one can actually determine the equilibrium values of currents in any chiral CFT, and that's the answer you get. So you get the expectation value of a electric current operator is just proportional to the chemical potential, no dependence on temperature, while this is what you get for energy current, no mixed terms. So therefore, this guy should be 0. Okay. So now this is a good argument, assuming that the edge is described by CFT, by unitary CFT. However, I mean, when I was first started thinking about this problem, which was like a year and a half ago or so, the question was this: suppose, could it be that there's some anomaly of the edge modes which forces the modes to be described by some weird field theory which is not even a CFT? So there's no general rule which tells you that the edge must be described by conformal field theory. Perhaps there are some intrinsically non-relativistic field theories, which anomalies, which cannot be realized in a CFT. That would be really interesting. So, so what is the motivation to look for other arguments? No, so here's an argument which is completely macroscopic. So one can first, by the way, in the literature, if you look at the literature on thermoelectric coefficients, not the transverse ones, which are kind of exotic, but the usual ones, the longitudinal ones. The one which describe the famous Seebeck and Peltier effects. But interestingly, Seebeck's work preceded Ohm's work. So Seebeck first discovered that you can get electric current out of temperature gradient based on some totally wrong understanding of physics. He thought that the temperature gradient somehow magnetizes his material. He had like a little magnetized needle, just like Ørsted did, and he put it next to a ring made of two materials, I think like copper and bismuth, and had some temperature gradient, and noticed that the magnetized needle deflects. And then he's like, oh, okay, then temperature gradient magnetizes my system. Well, that's not what happened. There's a current flowing. But anyway, so it was before actually Ohm's work. And Ohm actually used Seebeck's discovery because he didn't have any way to measure electromotive force, so he used the temperature gradient as a substitute for electromotive force. He actually studied dependence of current on the temperature difference. And that's how he came up with Ohm's law. So anyway, so this Seebeck-Peltier coefficients are, of course, much more familiar. That longitudinal thermoelectric coefficients, and there's often a statement in the literature that they must vanish at zero temperature thanks to the third law of thermodynamics. So, and the question I want to ask is, does it apply to the transverse thermoelectric coefficients, which are called nu and eta, which is not even usually discussed in this context? Well, first, let's let me remind you the third law of thermodynamics, which somehow not really used all that much, but it turned out to be very crucial for us. First of all, there are several formulations. They're not really equivalent. The most general, one is called the Nernst unattainability principle. It's a rather tricky statement. So it's a dynamical statement. It says that it's impossible to lower the entropy of a body to its zero temperature value within a finite time. Something about dynamics, something about time. Now, that sort of presupposes that the entropy at zero temperature actually is finite. That's sometimes called Einstein principle. Like things like, say, Boltzmann gas actually violate Einstein principle because entropy of a Boltzmann gas actually minus infinity at zero temperature. So, now, of course, in real life, there's no Boltzmann gas. All gases are quantum, and at low temperatures they become quantum, and then temperature indeed approaches a finite value. So anyway, so this is some dynamical statement about the impossibility of lowering temperature. So what is the status of this? Why do we need to postulate it? Can we just derive it? Well, if you formulate it this way, then it's actually not clear, not easy to understand how to derive that. That's why we need to postulate it. Some other formulations seem less amenable, more amenable to like proof, but this one, which is dynamical, is not so clear. So that's why I want to postulate it. But basically what it tells you, it basically closes a loophole in second law. The second law says that it's impossible to construct a 100% efficient heat engine, except if one of the reservoirs had zero temperature. So, but this third law says, well, second, you cannot have a reservoir with zero temperature. So you can never have 100% efficiency. So, okay, so why does this imply, why does this law imply vanishing of maybe transverse coefficient? Well, or does it maybe? Maybe it doesn't. So here is a standard expression I lifted, I think, from Landau and Lifshitz on the entropy current in such systems. By analyzing a little bit the hydrodynamics, you can figure out what the entropy current is. It has two terms. One is coming from the heat conductivity, and the other coming from electric field. This is in a stationary state, assuming everything is time independent. And now suppose I have two bodies called A and B, and connected with some material which I want to prove that this guy vanishes for zero temperature. So, well, actually, I've already argued that this guy is related to eta divided by t. So one can prove one or the other vanishes. That would be good enough. So now I'm going to try to create an entropy pump from which would make like entropy flow from B to A or from A to B. And the way I'm going to do it, I'm going to just put on electric field and some random angle, doesn't matter what it is. So and temperature will be the same. So I just want to pump entropy using this term. Well, we know that from the third law that when temperature goes to 0, entropy pumped per unit time should actually vanish. Otherwise, you'd be able to empty this reservoir, say, of entropy in a finite time. That, if you actually, well, what matters here is the net current, not this current, entropy current density. So when you integrate this over sort of a section of the system, you can check that what this really implies the symmetric part. Actually, not just of this little of this guy, because it's what occurs here, this ratio. The symmetric part of this tensor must vanish at equals 0. But by itself actually doesn't tell you anything about antisymmetric part. Well, so okay, so we sort of verify what people usually say, that the symmetric part of this thermoelectric coefficient should vanish at 0 temperature. But what about well, by the way, and then well, once you know that symmetric part of this vanishes, then you can also conclude about the symmetric part of this vanishing, because as I already mentioned, they're related. But what about antisymmetric part? I call this eta A, like for distinguish from the symmetric part. Now, there's actually an additional consideration which helps here. Actually, two considerations. First, one is called the Strata Formula. So it turns out that there is some formula whose status, by the way, is not really well understood theoretically, but it's out there. So there are actually two such formulas. One is that there are thermodynamic formulas for Hall conductance and for this thermoelectric coefficient nu. Actually, this formula essentially contained in this paper of Obraztsov, which are much earlier than Strata. So the two formulas. So I'm going to focus on the one for the thermoelectric coefficient. So it says that the thermoelectric coefficient at temperature T is proportional, well, it's just equal to the derivative of magnetization with respect to temperature, or using Maxwell relation of entropy density to with respect to magnetic field. Now, this formula is actually not exact, but it takes into account exactly only edge currents. But if you assume that the bulk contribution is exponentially small, that should be good. And well, that's one ingredient. And second ingredient is something called Nernst heat theorem, which actually historically preceded Nernst unattainability principle. So, like Nernst proposed this first as the formulation of the third law, and then Einstein criticized him. So he said, "Wait a second, I want to strengthen a little bit. This is not. I want to replace it with something else, namely with this unattainability principle." So the Nernst heat theorem is purely, it's not a dynamical statement, and in principle more amenable to proof. But nevertheless, I stated as it is. So as a sort of principle, even though it's called heat theorem, because originally Nernst thought he knew how to prove it, but actually later decided that maybe he doesn't. So the statement is that the temperature at zero, the entropy at 0 temperature becomes independent of the parameters of the Hamiltonian. And this, we want to argue then that this implies that these two facts, Strata Formula and the Nernst theorem, imply that this transverse and symmetric part of the thermoelectric coefficient also vanishes. So here's a little thought experiment. So here's our material of interest, again in orange. I now make a sort of a cylindrical shell, well, maybe elliptical shell out of it. And I put a solenoid through it. Okay. And I put magnetic field here. Now I also make inhomogeneous material. So you see, I cannot put, I would really like to put a monopole inside, but I cannot do it in a continuous way. But so I'm gonna put a solenoid instead of a monopole, so that there's no net magnetic flux through the surface, So, but there is a positive magnetic field flux here and negative magnetic flux here. So the net flux is 0. But then I make material inhomogeneous. So that on here, I'm going to have material of interest on this side. And here I'm going to have a trivial insulator. Now, you could ask me, how can interpolate? Well, because in general, when you have non-trivial material, you can have some edge between them, like right here. Well, suppose there's an edge. It doesn't really matter for me because I'm going to be always working at positive temperature. And positive temperature, there's nothing dramatic happening, even if you have an edge, in the sense that all correlators still decay with distance and stuff like that. So, so let's use the Strata Formula. So Strata Formula tells me that derivative of entropy, the spectromagnetic field, is proportional to the difference of these coefficients here and here. On the other hand, this Nernst heat theorem tells me that actually this becomes 0 at 0 temperature. And then I see that this must be equal to this at 0 temperature. Well, I forgot to mention that Nernst heat theorem actually follows from Nernst attendability principle. Nernst principle is stronger than Nernst heat theorem. Well, okay, with some assumptions. So, but anyway, this has standard assumptions like positivity of specific heat. Okay. So if you assume the third law in the first formulation, you actually get this essentially for free. So, and then if you combine with Strata formula, get that this must be equal to that at 0 temperature. Saying, well, there's one strange thing here that.
Anton.
Yeah.
Sorry, the previous slide.
Yeah.
What's the difference between the Nernst heat theorem that you write in the red color compared with just the law of thermodynamics? Is that are there differences?
Well, this is a thermodynamic. This is a principle about like a static theorem that the third law of thermodynamics is often stated like this, but actually it's actually a bit weaker. What you would like to know to have is this. So this is stronger, and that's actually is the correct form. Like people often confuse the two statements, but this is actually the correct formulation. They're very closely related, but you can try to prove this starting from the other guy, but that actually fails. That's not really possible, and there are some counterexamples. So, and that's an example. Look at Bose gas. Like it's kind of idealized situation. Like idealized Bose gas, it satisfies the Nernst heat theorem, but not Nernst attendability principle. Of course, a bit pathological system. Ideal Bose gas is pathological, but just keep in mind that this is like the most general formulation.
So is one of them more stronger, more general than the other? I'll just make sure.
This Nernst attendability principle is stronger than the other, and you can tell it's stronger because there are some dynamical issues. So the other statement about vanishing of entropy of a body being independent of temperature, that's I mean, there are no parameters at 0 temperature. That's a static statement. It should be easier to prove, and it essentially can be proved. But this is much harder. So that's why we invoke it as a principle.
Okay.
Yeah. Anton, may I
have a question?
Yes.
Sorry. I just didn't understand the geometry that you were showing in the previous slide. Could you bring it back? Yeah. I'm trying to understand what is going on here. So your two-dimensional system is wrapped around the. It's wrapped into a cylinder, if I understand it correctly.
Yeah.
And then you have a magnetic. But it's supposed to be a Hall conductor. So what's happening is your solenoid has a non-uniform current or something, so that
I guess my
the magnetic field isn't just what you indicated here, but it's also escaping from the sides. Is that what's going on?
Yeah, let me actually. It's a bad picture. Now that I see it, I realize it's a bad picture. So let me amend it a little bit. So what I want to create? Yeah. So this is actually what I want to create here. I want to create a situation. I have a cylinder which is capped off. So, and on this end, on one end, you have I have my material of interest, and here I have trivial insulator.
Okay, but it's capped, you're saying.
It's capped. And I just have a solenoid inside.
Okay.
So they have magnetic field escaping like this. So I subject one cap to magnetic field and the other cap to the opposite magnetic field.
Yeah. Mm-hmm.
Okay. And then on one hand, the magnetic field exists only in these regions. So you get that, the entropy is just related to the difference of these Nernst coefficients. Okay. Now, it's impossible actually to measure Nernst coefficient by itself, and we'll see why. Well, this new A. Later in part 2, we'll discuss this. So, in more detail, but you see, in this particular case, it's very clear that you can, unless you have monopole, you cannot measure just a nu of any particular material. And monopole will be problematic because you cannot continuously turn it off or turn it on. Its charge is quantized. So that's why I'm using this setup with no monopoles, but here we can switch off magnetic field continuously. Okay. So from this and this, so from Nernst heat theorem and this Strata formula, which by the way, again, it's it's a hand-waving argument for Strata formula. You get that this Nernst guy vanishes at 0 temperature if you normalize the Nernst coefficient of a trivial insulator to be 0 identically. So I'll talk about this later, why this normalization is unavoidable. And anyway, once you have this, you can invoke on Sago reciprocity and conclude that also the Eddingshausen guy is 0. Okay. So that's good. So now we know that for any system which obeys the third law, I cannot have non-zero nu A or 8A over T at 0 temperature. So no weird currents on the edges then.
Anton, before you continue, this is Andrei Nevedomsky. Can I ask you a question about the third law? So, you clearly thought about this and looked at the literature, which I haven't, so I apologize. But I often hear the third law of thermodynamics being stated as the fact that at 0 temperature, the entropy per volume has to go to 0. So is that just sort of historically incorrect statement, or does it follow somehow in a clever way from the heat, from Nernst principle and attendability principle?
Well, first of all, Nernst heat theorem itself can be deduced from Nernst principle. So that's can find in many older textbooks, the derivation. And Nernst heat theorem says that that your entropy of a body just is some constant independent of any parameters at 0 temperature.
Right, but I heard a stronger statement that it's not just a constant, but the constant is 0.
Well, within thermodynamics, it's impossible to define entropy except up to an additive constant. So this looks like normalization condition. Mm-hmm. So within thermodynamics, you always define it up to a constant. It's really the differential of entropy, which is defined.
But just to be clear, you'd want to rule out, systems that had some kind of extensive ground state degeneracy or something. No?
Yeah, but again, I'm sticking with thermodynamic description, and it's again this law. Well, yeah. So this degeneracy somehow makes no contribution to any thermodynamic considerations. So I'm not sure how to rule it out.
Okay. So you're saying right?
Yes.
I mean, I was thinking about spin ice or something where you have, in principle, some non-zero 0 temperature.
Well, I guess if you're literally at 0 temperature, even everything will freeze over. But in some range of temperatures, you could have situations when the entropy appears to be constant and extensive. That happens. Yeah.
Doesn't water ice do that as well?
Sorry?
There's also extensive degeneracy in just water ice, but no thermodynamic signature of that.
Yes. Yeah.
Well, you have a question of whether you've really reached equilibrium or not. I mean, it's always orders of limits of how perturbations that break this degeneracy, how large they are versus how slow you're cooling it, and whether you're willing to wait as long as the age of the universe, etc. So in practice, you're never really exploring the thermodynamic ground state of any ice or glassy system.
Right. By the way, so I guess regarding to that, order of limits is a subtle issue here. I'm not sure, for example, if the following statement is true or not. Namely, here, Nernst talked about entropy of a finite body and zero temperature limit. It would be more useful to have some statement about entropy density. So that is first take the limit of infinite volume and then take the limit of temperature goes to zero. I'm not sure to what extent that's equivalent. So this order of limits issue usually bothers me. Okay, so let me just give a third argument. So argument number 3 was our attempt to give a microscopic argument for this Nernst, vanish of Nernst was nu A or 8A at zero temperature. I don't want to go into detail because it's kind of lengthy. And anyway, it's not satisfactory because all these holes somewhere in the way which we weren't able to close. The setup used here is kind of a Laughlin type argument. So now we consider some isolated system made of this material. Now it's homogeneous. So here it is. Make a cylinder out of it. And there are now edge modes on these edges. And now I put a solenoid, indeed, and insert 1 unit of flux and see what happens. And then there is some current flowing. Well, there could be some current flowing in this direction, or a heat current if there's this eta coefficient. When the electric field is generated this way, right? So the heat current would flow in some way like that. Now, but nothing happens in the bulk. The bulk remains undisturbed. All that can happen is some change in the density matrices of the edges where the gapless modes are. And then one can show, though, well, that's where the loopholes are, that the entropy changes on both edges are actually positive, or at least not negative. On the other hand, we expect this is a adiabatic process, so entropy probably shouldn't change at all, right? So we must have something like this. And then the conclusion is that the change in entropy must be 0, actually. So the combination of these two guys, this means they just must separately vanish. And that means then that this Etingshausen guy, which controls the flow of entropy along this cylinder, must vanish. Now, as I say, there's some holes in this argument, but at least an attempt to do it macroscopically. And this gives some more information because actually allows you to argue that actually this guy not just vanishes, it actually should be exponentially small at low temperatures. That's something which doesn't follow from the third law or from this conformal field theory considerations. I should say one more thing. Identical arguments essentially identical can be used to argue that there can be no entropy analog of the Thouless pump. So what's the situation I'm considering? It's a similar situation. I'm just compress this cylinder into just a 1D system. Suppose it's gapped and at low temperature. Now, suppose I now vary the Hamiltonian periodically. That's a bit more general than the previous case where just vary flux, insert a unit of flux. So suppose I just have some abstract parameter and I vary it periodically, and I'm asking whether a finite amount of entropy can be pumped through the section of a system. Now, of course, Nernst principle says it cannot happen. If it could happen, I could beat the third law. I could violate the third law. But the microscopic argument that we gave for the case of Laughlin's sort of type of deformation of the Hamiltonian actually, applies also to the more general paths, and it shows that this actually does not happen. That is, you don't pump entropy at low temperatures. So there's no Thouless entropy pump. But again, it's a plausible argument, but it's not rigorous, not even close. Okay, so part 2 of this talk. Well, if there are questions about part 1, so let me take questions now because part 2 is going to be a bit more, a bit different. Okay, so in part 2, I'd like to address another old question, which is much older. That's a work which is not out yet. Namely, how does one write down well-defined macroscopic formulas for these thermoelectric coefficients? Now, we want a general formula, and such general formulas are usually known as Kubo formulas. And the formulas for thermoelectric case were written by Lattinger in 1964. So a really old work. Now, Lattinger made some errors in that paper, some conceptual errors actually, and these were largely fixed by Cooper, Halper, and Rosen in '97. And specifically, they noticed that transport coefficients, some of them, not all of them, receive contributions from magnetizations. And that's basically an edge effect. Now, these magnetizations, unfortunately, are ambiguous. So they're defined in some way which leaves ambiguity there. So, but one can actually derive formulas for derivatives of magnetization. Okay. And with some normalizations, one can get formulas for transport coefficients themselves. Now, there's still remaining some defects in this chain of reasoning, and I'd like to describe our understanding of this issue, which I think is more general. So, what did Lattinger do wrong, in our opinion? Well, first of all, as I already mentioned, he did not take into account edge effects. But that was largely fixed by this work of Cooper, Halper, and Rosen. Now, however, what is another thing which is a bit harder to fix? Lattinger assumed a simple dependence of currents, both electric and energy currents, on external fields. Now, this dependence does not hold in general. It does hold for free systems, but for interacting systems, it usually doesn't hold. And one can try to find the right currents for any particular system for which this depends, well, this assumption is satisfied, but it's not clear it exists. And it's not even clear why you should assume that. So why don't just it shouldn't matter how you choose currents. It's well known in field theory that currents are ambiguous, but it doesn't cause any physical issues. So why should we look for some particular current if any current should do just as well? So now, also, it's actually turned out to be actually easier to work with lattice systems rather than continuous systems, because for lattice systems, they're completely general expressions for currents. But for continuous systems, well, they depend on the Hamiltonian and some details of Hamiltonian. And for lattice systems, we'll see that one can just work with essentially the generic systems. And however, one discovers some new terms. But one doesn't need to tune your currents to satisfy any scaling relations. But one can then one pays a little price. One finds some new terms in Kubo formulas, even for dissipative transport coefficients. Okay, so here's how I'm going to think about a lattice system. So here's my picture of a lattice. So just a bunch of points in Euclidean space. No regularity is assumed. I just assume that the points, don't accumulate anywhere, and then they don't spread out farther and farther as you go to infinity. Such a set is usually called Delaunay set in mathematical literature. So what is a current? Well, I first of all look at particle number, and it's just some U1 symmetry, and I assume that, as usual, the charge is written as a sum of local terms, on-site terms. So each NP just acts on site P in this lattice. Now, we're typically given this decomposition. But energy is a bit harder. So energy, well, the Hamiltonian also can also decompose into these local terms, but typically nobody tells you how to do that. So it's not uniquely fixed. So this H of P acts in some neighborhood of some site P. Or maybe not even a neighborhood, maybe there's some decaying interactions, and then this decay is maybe exponential or whatever, but so HP is not strictly localized at site P. Now, what is conservation equation? How do you find currents in a lattice? Well, by definition, a current should be what controls the rate of change of a charge on some site. I guess I switched my notation, sorry. I switched from N to capital Q, sorry about that. So you see that, well, natural definition is like this. So you look at the time derivative and you want to write it as a sum of flows from all other sites so you have this JPQ is going to be flow of charge from P to Q, or minus flow of charge from Q to Q. P. So there's this equation, which is a lattice analog of conservation equation. And similarly for energy. So whatever solution you have to this equation, this GE is going to be your current. Now, it's actually a canonical expression for this, sort of obvious expressions for this currents in the lattice. Once you have this decomposition, you can just write JE like this energy current from Q to P.
I'm sorry, but locality of interaction, it's kind of not, it doesn't look like very well defined, right? Because you can have interaction, between different points, in principle far away, right? So I mean, when you're saying it's local Hamiltonian, right? I mean, what you're implying?
Well, it actually depends on the problem, but basically implying this H of P involves, it might involve a sum over lattice sites, but the contribution of sites which are far from P is small. Okay, so
yeah, but the range could be arbitrary, right? It could be very large, for example, or it doesn't matter.
Well, it does matter. Various things become ill-defined if this. Well, basically, I want to say that suppose you look at the H of P, and look at the commutator of H of P with some local observable at some site far away. So, right. So you want this commutator to be small, right? Mm-hmm. How small? Well, depends on the problem. Like for example, if it's exponentially small, it's good enough for all purposes. If it's small only as a power of a distance, then the power matters. Mm-hmm. If the power is not high enough compared to the dimension, you might be in trouble in the sense that various formulas become ill-defined.
Okay. So, okay. Thank you.
Yeah. So I want to assume that typically for theoretical reasons, it's usually enough to assume that these commutators vanish faster than any power of the distance. That's good enough for all purposes. But concrete powers also occur, of course, and they're important.
So, just make sure the discussion Arkady asked is about whether there's a local Hamiltonian with short-range interaction description. Is that the essence?
Well, I'm assuming, yeah, I'm going to assume that my Hamiltonian has short-range interaction, but what that exactly means is like open debate.
Bound with the interaction bound with some distance. Like
some power of a distance should be good enough, really. But which power it is depends on dimension.
Okay.
So as a result, this current operator, say energy current, has very simple canonical form. But it now depends on two sites. It's not like in continuum, a current is a vector, but here it's a function of two sites. Same goes for particle current or U1 current. So now what are these properties of these objects? Well, the first of all is symmetric for reasons they already mentioned. Current from Q to P must be equal to minus current from P to Q. And must also vanish if the P is far from Q. That's again assured because this locality condition on H. These commutators become very small when P and Q are far apart. And second is localized near P and Q, this object. And by the way, notice this sort of taking divergence of a current becomes a very simple operation in lattice, just summing over one index. It's an analog of divergence. This sums. Now the currents are ambiguous. That's true in field theory and it's true in the lattice. But in the continuum, you can add some divergences to your currents of some high index tensors. On the lattice, you can do this. You can add to some sum of some other local object, namely, again, should be skew symmetric. It must vanish if P is far from Q and R, and it must be localized near these points. So it's easy to check when you sum over P. Because of skew symmetry, they just will drop out. So you can always modify current like that. And all physical quantities, though, must be unaffected. So when I construct something physical, we better make sure that this doesn't affect anything. And another thing which we need to worry about is ambiguity in decomposing H into the sum. Again, nothing physical should depend on it. Well, it's an example of a physical quantity which doesn't depend on such thing. Well, for example, net current across a line if you're in 2 dimensions, or across a surface if you're in 3 dimensions. Let me stick to 2 dimensions. So here's my lattice. I draw this line, and I want to study the current from B to A, like this. Well, I just formed this sum. The sum of flows from Q to P, where Q is in B and P is in A. But I forgot to say that this way of thinking about currents actually is due to Kitaev. In his paper on anyons and exactly solved model, he explained this in one of the appendices. So, well, another way to write this with this formula, which I prefer for some technical reasons, is as a double sum over the whole lattice, but weighted with some function of two variables. So here and below, I'll denote by theta of B a function which vanishes when argument outside set B and is 1 when it's inside set B. So there is it's called characteristic function of a set. So you can check that this is the same thing. You can just take all these currents labeled by points, multiply by this guy, and sum, and this is the same as a flux. And that actually is a finite sum if this because of this decay condition. When P and Q are far from each other, this guy is just small. So when we sum like this, first of all, P must be on one side, namely here, and Q on the other side. On the other hand, they must be close together. So the only way to do this is when you're localized near this region. So that's why you get a finite sum, provided, well, somewhere this closes off in some finite region. Okay. So how we're going to use this can be used to set up a new way to compute the derive a new type of Kubo formulas. So so here is how I would like to derive them. So I'm going to create a disturbance, but I'm going to create a disturbance not in the whole space, but only in some region. This one. Say I want to maybe the temperature is going to be different up here than compared to here. So this is where the temperature gradient is going to be. Say here temperature is constant, here it's constant, but here it changes. I want to measure the current flow in the perpendicular direction. So I pick some line, it doesn't even have to be straight, some line which is approximately straight, and compute the current in this direction. And then standard type arguments, like in Lattinger's paper, or Kubo's paper for that matter, tell you that the current in non-equilibrium steady state is going to be given by some double integral. You need to integrate over imaginary time and then over real time. And here I denoted JRL is this current operator from left to right, and GETB turns out to be represents this perturbation. It's the current from bottom to top, like from here to here. So now this could be current, either electric or energy. While since I chose the temperature to be the driving force, this is always electric. This is always energy current. So that's a naive formula, but there are a couple of subtleties here. Well, this will give a naive Kubo formula, but that's a bit not quite right. First of all, this ignores the contribution from the variation of the current operator. Okay. This part just tells you why the expectation value of the current changes because you're in non-equilibrium steady state. It's a change in the density matrix. But this part, it should be also part which comes from explicit variation of the current operator itself. And second, this ignores that equilibrium currents themselves depend on temperature. I need to subtract somehow those out to get the transport current. That was the part which was dealt with in the paper by Cooper, Halper, and Rudin. Now, let me remind you what this means. Like typically when we write in currents in the continuum, well, you write them as a sum of transport currents and magnetization currents. Magnetization currents are curls of magnetizations. So there's a magnetization of charge and the less familiar magnetization of energy. And I'm in 2 dimensions, so this curl, well, in my case, M, N, and M are just scalars, and their curls are just expressions like that. Now, one thing which should be kept in mind is that this decomposition is ambiguous. It's really only this guy which is physical, or more precisely, its integral is physical. But anyway, this guy is physical, but this decomposition is a bit arbitrary. say, say, look at, say, an electric current, that's the form. You can always the transport current. You can always redefine magnetization by some function of temperature, and simultaneously shift your electric current, and nothing changes, right? This total current doesn't change at all. But this redefines the transport coefficients. It replaces this guy by some skew-symmetric part. So that's why the skew-symmetric part is, strictly speaking, not a physical quantity. You can also absorb a part, or actually you can absorb all of it into magnetization current. So we say it's a relative transport coefficient because even though you can absorb it, the differences of these transport coefficients for different materials are still well defined. So similarly, skew-symmetric parts of this and this can be absorbed. However, it turns out this difference, by the way, because the same sort of redefinition of magnetization removes this guy and this guy. Oops. And this guy, with only one function, this one. So you cannot remove both. So this combination turns out to be well defined, sort of absolute. And that's not actually, it's a good thing because it actually appears in the expression for the entropy production rate. This part is a well-defined thing. Anyway, let me just state the resulting formulas if you do it right. So for Hall conductance, nothing really, everything turns out to be okay. So this is the right formula in all circumstances. But for other transport coefficients, life is quite a bit more complicated. So in fact, it's better to deal with symmetric parts first. So we have this thermoelectric guys and the thermal conductance, and look at the transverse parts. Well, so first of all, the symmetric part of thermal conductance doesn't change at all. It's like still the naive one. But for the thermoelectric part, there's an extra piece.
So, excuse me, what do you mean by symmetric if it's new xy? Symmetric in what variables?
In x and y. You have a new xy and have new yx. So you take the average of the two, it's called symmetric part.
Okay.
So the symmetric part of the conductance given by the standard Kubo formula. But the symmetric part of this guy is not, in general. There's some extra piece here. So what is it doing there? It's a local piece, unlike the previous guys, which this guy is also integration over time. So, sorry. So yeah, this piece is local. So what is it doing there? Well, it's actually necessary to ensure that this physical quantity, which actually enters the entropy production rate, is independent of the choice of the way you decompose the Hamiltonian into these pieces. One can check that if you replace, so what is the ambiguity there? Well, I can also replace H like this, because when this is skew-symmetric in P and Q, when you sum over P, it's just going to drop out. So this does not change the total Hamiltonian, but it does change the currents. But the physical quantity shouldn't change, right? You can check that this correlator actually does change, but this guy just cancels this out. So this is a general formula. So surprisingly, somehow here that doesn't happen. So here everything drops out. So you don't need extra pieces and they don't occur actually.
A question.
Yeah.
What is S in these exponentials?
Sorry, I forgot to mention. In Kubo formulas, there's also some little parameter, which take it to 0 in the end. I omitted this symbol as goes to 0 limit. There should be a limit sign out here.
Anton, also a question, when we were talking about definition of the current in terms of particle physics, I would be compare, you have this charge term, and you can have terms which are like a magnetic moment, in the current. So other multiples, right? And multiples are not, associated with the change of charge, right? Because, but why I'm asking, because in principle it could be, you know, many multiples, right? I mean, for say spin 1/2, you have magnetic moment, but for spin 1 you can have quadruple and so on. But maybe my equation doesn't make sense. I just, you see, but I imagine that the current is just refers to monopole part. I mean, in a sense, when you're integrating out.
I just meant the current which solves the conservation equation. So time derivatives of charge density must be equal to minus divergence of the current.
Yeah, I agree, but right. But in this way, part which is higher multiples do not contribute to the charge, right?
Well, they do. Well, yeah, they don't contribute to the charge. Yes. So you know, when you define current, you just formally take derivative with respect to external field, right? That's one way to
right, but say high multiples, they do contribute to selection of the external field, but they do not contribute to the charge, right?
Yeah, such things do not affect things like conductances, for example.
Yeah, right. So in this way, it should be some kind of quite a number. If I'm trying to classify deviation, right, then I should do something like a multiple analysis, you know, in these terms, right? Because it could be, you know, in this way, depending on what kind of object we are considering, it could be quite a number of them, right? I mean, if they have internal features like spin or whatever.
Yeah, I mean, certain things will not, certain couplings of external fields to your system will not affect things like transport coefficient,
Yeah, okay. So in this way, you are kind of agreeing with this point, right? That it is kind of higher multiples which do not contribute to
yeah.
Okay,
great.
Thank you.
Yeah, you could consider maybe transport of dipole moment or something like that, but I'm not doing that. So I'm considering on transport of charge. Okay. So anyway, so it turns out that there's a simple way to fix this, but only somehow affects this thermoelectric coefficients in nu and eta. So that's true even for symmetric parts of these tensors. Now the skew-symmetric parts are a bit trickier. So as already mentioned, there's a monetization current contribution which needs to be taken into account. So there's a hole, the thermal hole, Nernst, and Ettingshausen effects in the four skew-symmetric guys that antisymmetrize in X and Y. Now the naive Kubo formula does hold for hole conductance, but as explained this by the authors, you need to count magnetization currents in all other three, these guys. Now, one thing which I'd like to deal with is that these authors assume the simple scaling behavior of these currents to derive these extra contributions. So they assume that the energy density transforms in this way under, well, suppose you rescale energy density like this by overall factor plus add some charge density with some electric potential. So they assume that the particle number current transforms like this, while the energy current transforms like that. Well, it seems pretty like well, for free systems, that's the standard definitions are indeed such that this holds. But for general interacting systems, that's one needs to look hard for such a current, and it's not clear that it exists. And in any case, for lattice systems, which do have sort of more canonical expressions, and we'd like to use those, not to try to adjust our definitions on a case-by-case basis. So one can instead just re-examine the derivation for lattice systems and for general currents and take this into and just it turns out you can easily get formulas even for general currents. You don't need to assume any scaling relationships. So the trick is the following, at least the way we do it. From our point of view, all these weird transport coefficients which are affected by edge effects are relative coefficients. That is, the only differences for different materials make sense. So then we do the following thing. So we make our system inhomogeneous. So in this direction, in this direction. So we have two different parameters for Hamiltonian. And we temperature is the same both here and here, but it's different here. So we have two regions with this temperature gradient. And then there's some current flowing here as well as here. But the temperature gradient is opposite in this region compared to this one. So what this setup measures is the difference of transport coefficient in this region and in this region. And that's good enough because that's what we want to compute. We don't want to compute absolute values of transport coefficients, just their differences. And we can actually take this, change infinitesimal, so we get directly formulas for derivatives of transport coefficients. So here's a formula, for example, for this Nernst guy, for this Q-symmetric part. So there's a derivative of the usual Kubo type form. And then there is additional sort of local term. And it involves some tensor in quotes, because it depends on 3 points in the lattice. So each point, each guy is a differential in the parameter space, but it has some properties in P, Q, and R. It's a Q-symmetric in P, Q, and R, decays rapidly when all these points are far apart, and so forth. So explicit formula for this here. Okay. So it doesn't involve integration over real time, it's just some local thing. Incidentally, how do I know that this decays rapidly? Well, that depends on the fact that ordinary correlators decay rapidly. If I am away from phase transition, then all correlators of local observables decay rapidly when the points are far apart. And then I can show rigorously, a student of mine just showed it last year, that if you ordinary correlators decay, then using KMS condition and the Lieb-Robinson bounds, you can show that this imaginary time average correlators also decay. So we know these guys decay away from phase transition, which is good because we only want to set up transport theory of this sort away from phase transitions. So this is a formula which applies, which is well defined. I provided this term, of course, is well defined, which is tricky, but this is certainly this term is well defined. And it has a pleasing property. You can check that if you change your decomposition of Hamiltonian to a sum of Hamiltonians, this changes again, and this changes, but the differences cancel out. Now, what is this weird object with 3 indices? Well, that's actually related to magnetization, but on the lattice. So I already sort of convinced you, I hope, that objects with 2 indices, 2 points, depending on 2 points in the lattice, are physical, they're currents. Turns out that objects with 3 indices are magnetizations on the lattice. Let me explain why. So in the continuum, magnetization, well, you have this formula for the average of the current. In a steady state, expectation of current must have vanishing divergence, so you can conclude that there's something called magnetization, which in 2 dimensions is the formula. And similarly for energy current. Now, what's the lattice analog of that? Well, on a lattice, the condition of being stationary means this. If you pick some site, the flow of whatever, of stuff into the site must be vanished in equilibrium on average. What does it mean on the lattice? Well, it's actually not so obvious, but actually one can show that this is a general solution. So, and that's why this object is kind of analogous to magnetization. And just like there's ambiguities. In the continuum, ambiguities and magnetization simply shift by a constant. On the lattice, well, it's a more weird thing. You can shift this guy with 3 indices by a guy with 4 indices. Okay, whatever. In any case, you don't ever deal with these guys individually. You always contract with something, and then these ambiguities don't matter. In any case, this guy is still ambiguous, just like shifting by constant is ambiguous. But what's unambiguous is differentials. You can write a formula for the differentials of this magnetization, and that turns out this guy, which enters the formula for conductances. And so this way you get explicit formulas for derivatives of all these relative transport coefficients with respect to parameters. And that's good enough. That's all one needs to know, because then one can integrate and get differences for any 2 materials. Let me just conclude with some remarks. So our version of Kubo formula is a bit different from the standard approach. In the standard approaches use averaged currents, and the currents are averaged over the whole space. So here, both currents which enter the formula. Here we average one current over somehow one line and average another current over another line. That actually it seems sufficient and makes things more well defined in the sense that you don't. But the issue is still there, like to what extent it's well defined. In a sense, even though it seems like you're measuring transport only in this region, in reality, when you take this little parameter s to 0, which you do at the very end, it looks like you average over the whole volume in the end anyway. So so in reality, it's some you actually measure conductivity in this way, not conductance. Now you could ask me, why did they fall? If it's such a nice approach, why don't I apply it to longitudinal transport coefficients? Well, for example, suppose I take a line which is not perpendicular, but measure current to this kind of line with some angle theta with the horizontal line. What I can do the same computation, nothing changes. So what does this measure? Well, this is supposed to measure, if you believe hydrodynamics, this combination. So by varying theta, I can, in principle, extract both transverse coefficient and the longitudinal one. Now, I'm actually not sure if this works, because if you stare at Kubo formula, it's not even clear why dependence on the angle should be like that. This is what hydrodynamics predicts, but what microscopic predicts, I have no idea. Well, whether microscopic matches that, that's not clear to me. So in general, I must say that this Kubo formulas, the status is quite complicated. The way people usually say that, well, we're just computing some quantity, which in macroscopically, and then the same quantity, which may be very unphysical, not very physical, using hydrodynamics, and match them. And that's how we extract transfer coefficients. What's not clear to me is why you can actually invent lots of such similar quantities, for example, by like tilting this line here. People just usually average currents over the whole space. Nobody forces you to do that. So you can average over some regions, you can apply all kinds of infinitesimal perturbations, and hydrodynamics makes some predictions about that. And it's not clear that microscopic formulas reproduce these predictions. And that's, for example, this kind of dependence on the angle is like an example of what you would like to see. I don't know how to see that and under what condition this holds. And let me summarize. So I argued that, well, I explained that how the third law makes predictions about low temperature behavior of transport coefficients, some of them. Now, they still hold, because in the sense that it would be good to prove some consequences of the third law rigorously. I don't want to rely on the third law. I want to derive these consequences rigorously. Well, same goes for the second law, actually. Like second law predicts that, say, some transport coefficients some positivity constraint on transport coefficients. On the other hand, there are these microscopic formulas for them, and we'd like to maybe directly verify those. Well, how do you do that? Well, we need to understand Kubo formulas better, for one thing. And the question number 0 is, why are they even well defined? Since they will involve integrals over time, that's far from obvious. And in particular, for example, we know that actually some of them are not well defined. For example, for superconductors, some transport coefficients like conductivity are not well defined. And how do I decide which coefficients make sense for which system a priori before doing any computations? I don't know. I would like to understand. And by the way, if you have some, I searched a little bit about transport properties of superconductors, not just what sort of transport coefficients you can actually use to describe superconductors. If some of them are infinite, maybe some others are also infinite. So unfortunately, I couldn't find anything useful. Maybe if anyone in the audience knows some discussion of transport and superconductors in a general level, like not for a concrete system, but in general, what sort of transport coefficients are well defined, I would be happy to know about this. Thank you.
All right, thank you very much, Anton. Great talk. We have some time for questions. If you have a question, you can just speak up.
Can I have one? I'm Maria Vozmediano from Madrid, and I would like to know if the first part of your talk would still apply if you don't have a gap state, but you have, say, like a semi-metal, would still be everything applying?
No, yeah, so depends on which part. So if you look at, say, things which are predicted by the third law alone, then yes. However, if you say things like, let's say the part which uses Strata Formula,
yep,
that's not so clear, right? Because Strata Formula, strictly speaking, arises by neglecting the bulk currents compared to the edge currents. So I don't think it will apply in the case like with semi-metals. So not clear to me like to what extent. Yeah, I know this is true. The part which is which uses Strata Formula, specifically the vanishing of skew-symmetric part of transport coefficients at low temperature. The symmetric ones are safe, so they just come from the Nernst principle. The vanishing and play with it. Yeah.
Okay, thanks.
Let's see. Can I make a comment or ask a question? First of all, as I said, it's a beautiful talk. It's very interesting, and I enjoyed it very much. It's just the last item about superconductors. Well, I'm not sure how much has been done in superconductors, but of course, for superfluids, the various transport coefficients that exist in that case have been very well studied, for example, by Landau, not in the presence of a magnetic field. So one could certainly ask about what happens if you have a broken, that kind of broken symmetry, but at least that part has been done. So there certainly has been stuff done there. And of course, things depend singularly as you go to zero temperature. I just wanted to make a comment that just partly it was maybe partly addresses Arkadiy's question as well, is that of course all these transport coefficients that we're talking about here are defined. We're looking really at what happens at large scale, sort of. It's a long wavelength limit. We're assuming that the system is very large compared to the lattice constant, et cetera, and all microscopic lengths. And the issue of how you define currents and so forth. Also, you can ask, at what scale are we really trying to define them? So if the charge current, of course, we know we can really define it on any length scale we want, because we know from just even from Maxwell's equations that that a current generates a magnetic field, and if you could measure the magnetic field, you could measure the current on any length scale. For of course, in principle, energy currents also are the source of a gravitational field, and in principle, if you could measure the gravitational fields properly, or look at the response to gravitational fields, you could define energy currents on any scale. But that, if you did that, then of course you would be using energy currents that have nothing to do with the usual energy currents we're looking at. For example, we know that if you have two currents, you'd be including not only the energy carried by the particles and their interactions locally, but you'd have energy currents which are spread way out into 3 dimensions from your 2-dimensional currents, let's say, because they're carried by the magnetic field, or E cross B, far away from the currents of the Poynting's vector. So, so indeed, as a practical matter, you always are going to have this ambiguity, as was pointed out, that you can add various the curl of some vector. You can add divergence-free quantities to the definition of your energy current, and it doesn't affect anything physical. So that of course complicates a lot of the definitions and complicates all these proofs.
Right. Yeah. Thank you. Yeah. So for lattice systems, yeah, it's easier just to work with some general current, just make sure everything works. So because you don't have to like adjust your current every time to conform to some particularly nice sort of gauge fixing condition. Because sometimes it's hard to find one which solves the right gauge fixing condition.
Right.
But I forgot to mention, for example, for the symmetric part of the tensors, these new terms which you found actually magically disappear for certain systems, namely for free particles, free fermions, they disappear identically with the natural definition of currents, and therefore they also disappear for for particles with only Hubbard-like interactions. You can show, like, if you're typically, if you look at your Hamiltonian, each piece in the Hamiltonian is invariant under commutes with the whole charge operator, but doesn't compute with on-site individual charge operators. But if you have like Hubbard-like interactions, it's a very special situation that interaction terms actually commute with each piece in the charge. They actually commute with the charge density. And for those systems, again, those new terms we found just become identically zero with the natural definition of the everything.
Let me just ask one very closely related question. So certainly, if you're looking at the symmetric part of the XY conductivity or whatever, I can make a 45-degree rotation, and then it becomes an XX or a YY. So I'm trying to, presumably you would find all of the same corrections and things you'd have to worry about if you were looking at the XX or YY coefficients. Is that right?
Yeah, the only trouble is that we cannot not strictly go to, we can only measure these angle dependent guys, right? So as I already mentioned, our formalism is geared towards situation when there's some mismatch between the direction of the current we measure and the direction of the gradient, like here, see? The mismatch must be there, otherwise things get out of hand. But just by looking at the angle dependence, of course, extract both longitudinal and they also, yeah, so this extra term is always present, right? In our approach. So somehow just artifactual approach, you cannot like literally align these two lines.
Can I go back to this point about the JT anomaly for non-unitary theories? You said there's no topological term that you can write for this, but I suppose if you are to distinguish a time direction, then it seems like you can write something like A times the Gaussian curvature of the 2D slice.
Yeah, it's true. There's no covariant term, but for some reason you might be able to write non-covariant one. Yeah, I'm not sure why that happens. Non-unitarity seems to have nothing to do with non-covariance. I'm not sure.
Yeah, that's
true.
true.
Why covariance should matter? It's not even clear, because anomalies make sense even in the absence of any like Lorentz invariance or whatever. Anomalous current. So one should be able to relax conditional Lorentz invariance and still get similar results.
Right, that's a good point.
Anton, question.
Yes.
I suppose the discussion today here mostly based on phenomena more related to thermodynamics and STEMAC, in the sense it's more finite temperature effects. So I was wondering, do you have other motivation that are more closely related to maybe quantum field theory or something else you are thinking? So you are working on this. That's just one kind of things you understand. Your other than tackle this question, are there some other things more related to quantum field theory you're thinking about?
Well, I started out this question simply because I want to test quantum field theory predictions. It's not clear to me why I should believe a quantum field theory, which when it says, okay, there are this many invariants, because that's how if you classify topological field theory and topological action, you get this kind of responses. It's not clear why this is the right thing to do when consider lattice systems, for example. So it's good to have an independent argument. That was the original motivation. There are, of course, more elaborate questions of this sort, like all kinds of, yeah, so you like to verify the more elaborate predictions of topological field theory, especially in higher dimensions. For example, a statement that if you have a short-range entangled phase, that, okay, first of all, if you want to show the thermal conductance, yeah, so it should be really quantized, right? Its Ehrlich slope, its term should be quantized in some way. It should be a rational number, and if you're short-range entangled, then it should be actually quantized in units of something. So that would be a more accurate test of predictions of field theory. That seems very hard, though. We thought about it hard for the last more than a year and came up with nothing.
Anton, I am kind of reacting to your comment about breaking Lorentz invariance. I would say that in certain anomalies, Lorentz invariance is crucial for deriving anomaly. Like, for example, this axial anomaly, you know, this Adler-Baldin, Adler-Beljakif that does depend on, you know, that you are implying Lorentz invariance?
I don't know. I think anomaly is more like conflict between conservation of current and locality. In
Right, but
relativistic quantum field theory, it's very easy to confuse Lorentz invariance with locality or causality.
No, but when you are writing kind of say stating some stuff like say that there is no, for example, certain spin like analyzing amplitude for triangle, then you are using Lorentz invariance explicitly because then it allows you to limit number of amplitudes, right? And that's why, you know, it enters, you know, in derivation itself. I mean, so in this way, when you see, when you can differentiate, you know, space from time, you can satisfy something with, easier than when you have Lorentz invariance which relates this.
That's a very interesting question. Which anomalies make sense even? Which anomalies remain anomalous even when you drop Lorentz invariance? I feel that some of them stay there even when you impose something much weaker than Lorentz invariance.
Right, but I'm trying to mention this axial anomaly as an example where I believe this Lorentz invariance is important.
Well, I'm not sure it's important, but we can discuss.
So we can discuss it separately, but I mean, okay.
Well, there are certainly non-Lorentz invariant systems with axial anomaly. You can take several Luttinger liquids with different Fermi velocity. That's an example.
No, right. But I'm this particular form of anomaly. You know, when you are discussing, say, pi 0 to photons or whatever, then you're using this Lorentz invariance for construction, and that's why I mentioned that. But okay,
you're talking about for the bulk term, because then you have something much stronger, which is topological invariance.
Yeah, no, but look, it's kind of, the question is that, for example, what kind of singularity you have? Okay, the axial anomaly implies that you have singularity at small q square. Okay, when we are talking about in terms of Lorentz invariant theory, okay, it's function of this one parameter q square, and that's it, right? When you are taking away Lorentz invariance, then you have just more possibilities just kinematically.
No, it's okay. So you're right. This question is interesting, but it's a bit but in 4 dimensions, it's a bit difficult to analyze. But in 2 dimensions, where similar things occur, it's much better understood, and it's clear you can formulate this in a very straightforward way without any using Lorentz invariance. Namely, as the presence of a Schwinger term, like a C number term, in the commutator of charge densities. So, and this statement has nothing to do with any Lorentz invariance. It makes sense in non-relativistic field theory, and that's an example of this strange analytic behavior when you Fourier transform to momentum space.
No, I'm not saying.
Presumably, similar things can be done in 4 dimensions, but I don't know how to do that.
Yeah, but I'm trying to say that it could be a little bit more mixed in terms of you know, what kind of consequence of anomaly you are discussing. Okay.
Well, if there are no more questions, we can stop the recording. You're free to go. Well, I have one more question, which is, can we see your T-shirt?
Okay.
Kapustin, Nikolai Kapustin.
That's excellent.